Hey kiddos, welcome to Unit 6. Unit 6 is where everything turns around and we start answering the second big question in calculus. So the first big question in calculus you didn't even know you were answering, but the first big question had everything to do with a derivative. And what does it mean and what does it tell you? And if you know things about it, what does that mean in context? So that's like if you're in college, that's Calc 1. Today we start Calc 2. So your second big question in calculus is how do you find the area under a curve? And I always say area under a curve. That's just the way it's phrased, but it's the area that starts on the x-axis and goes to the curve. So for this thing, if I just go between like -3 and 2, I would be trying to calculate this area here, so from the x-axis to the curve, and then this area here. So this would be negative area, which I know hurts your heart because you don't think there's negative area. Surprise, there is. So we're going to start today with something called Riemann sums. And Riemann sums are ways to approximate area under a curve. So remember back when you were in 7th grade and you were finding areas on planes and you sat there and you counted the squares underneath. I mean, we can do that, and that's an approximation technique. But you know, we have better ones. So this curve, you're going to need to know. I'm going to call it f of x, and this is the curve x cubed minus 13x minus 12. And the way, I'm just going to throw this notation at you, and I'm really kind of sorry about it, but the way I know where to start and stop my area calculation is with this new symbol. It is an integral symbol for those of you who know what that means. If you don't know what that means, it's okay. I will spend like 3 months teaching you about integrals. So we're going to go integrate. It looks like this. That's just the notation. So we're integrating f of x. And the way I know where to stop and start is the numbers that are here. So this is your start, and this is your stop. So we're going to do this 4 different ways. All 4 of them, I'm going to use the same start and stop so that will be the same for always. So this first one is what we call a left Riemann sum. A Riemann sum is a rectangle. You're going to add rectangles. Sorry, that's a dumb thing to say. You're going to add areas of rectangles. Okay. The other thing you have to know, so you have to know your start and your stop, and you have to know how many rectangles the question wants you to make. So for these first couple, we're going to do 3, and they'll tell you that in the question. So we're going to do what's called a left Riemann sum with 3, sometimes they call them partitions, so I'll say partitions. Sometimes they call them subdivisions. Sometimes they say 3 intervals, but 3. So we're going to make 3 rectangles. We're going to start at -2. So I'm going to put a big boundary here at -2, and we're going to stop when we get to +1. And we're going to go approximate the area under the curve with rectangles. All right, the reason it's called a left Riemann sum, here we go. If I start at -2, I guess the first thing, if I start at -2 and I go to 1, so I'm covering a distance of 1 minus -2, and I need 3 partitions to do that, then each of my partitions is 1 unit long. So what that is that's the width of our rectangles. So here's our first rectangle. It starts at -2, it goes for 1 unit. So this is the width, that's the base of our rectangle. This is a left Riemann sum. Because it is a left Riemann sum, we are going to set the height of this rectangle at the left function value. So here. So we're going to have this rectangle, and we're going to find the area of it, and that is our first rectangle. Our second rectangle will start at -1 and go to 0, so it still has a base of 1. And if I set I set the height of that rectangle to the left function value within this range, then it's just sitting at 0, so it has no height. My third rectangle will start at 0 and go to 1. And if I set the height at the left function value, it's going to have a negative height, and that's okay. So here is our third rectangle. And adding those together will give me what's called a left Riemann sum. So I'm going to put them up here, and I'm going to use approximating signs because these are approximations. The base of all of our rectangles was 1, so I'm just going to put the 1 on the outside. And then I'm doing area of a rectangle, so base times height. The base is always 1. The height of my first rectangle is, let's see, these are counting by 2s, so 2, 4, 6. So the height of the first rectangle is 6. The height of the second rectangle is nothing. The height of the third rectangle is negative 12. So we are approximating the area under this curve between negative 2 and 1 to be negative 6. Is it a good approximation? Nope. Not for this curve. It's really not. Because look, this is too much area in here because it extends outside the curve. This poor thing got ignored completely. And then the same thing down here. So I don't think this was a great approximator, but it's one option. And that's called a left Riemann sum because you use the left value. Here's your second choice. It's magically called a right Riemann sum. We're going to do the exact same thing. So we're going to go from negative 2 to 1, finding the area under that curve with a right Riemann sum with 3 subdivisions. Subdivision. All right, so negative 2 is our start. If I start at negative 2 and I go to 1 and I need 3 chunks to do it in, then each chunk must have a base of 1. Each rectangle is going to have a base of 1 again. So now my first rectangle starts at negative 2, goes to negative 1. This time I'm using the right function value. Well, that would be here. So that first rectangle has a height of nothing. Our second rectangle is going to start at negative 1 and go to 0. If I use the right value to create a rectangle, it's going to take me here down to negative 12. So I'd be finding all of this area. My third rectangle is going to start with a base of 1 again, but this height value is going to take me all the way down to negative 22, negative 24. And find all of that. So adding those up, this is approximating our area to be in negative 36. Is it a good approximation? No. Look at all of this excess negative area. This is excess negative area, and none of this positive area was taken into account. So I think negative 36 is much too low. Here's your next option. So I'm zooming through these because they're the same thing. One's on the left, one's on the right. Here's your next one. Your next one's called midpoint. Riemann sum. So we're still making rectangles. We're all Riemann sums. You're making rectangles. So this Riemann sum, first we did a left, then we did a right. Now we're doing a midpoint. We're going to start at negative 2 and go to 1. We're going to approximate the area under f of x. The base of all of our rectangles is still going to be 1. All right, but looky here. I already made dots for you. If I start at negative 2 and I go to negative 1, the midpoint of that region, not of your function, of the region you're in. So the midpoint between negative 2 and 1 is here at negative 1.5. And that function value is here. So that's where I'm going to draw the height of my rectangle. Do it again. Between negative 1 and 0, the midpoint there would be at negative 0.5. That function value is here. So that's where I'm going to draw, oops, it doesn't hit. That's where I'm going to draw the height of this rectangle. Same thing for this last region. That would be a function or a input of 0.5 to be the halfway, the midpoint. That's going to be here on my function. So there are my 3 rectangles that I'm finding the area of and adding together. Now, this approximation feels a little closer. So remember, if I'm going to go find all of this area, I have some excess area here. Oh, but look at this chunk that didn't get counted. Are those the same? I don't know, but it looks pretty good. Same thing here. I have excess negative area. Oh, but this chunk didn't get counted. So this Riemann sum, this midpoint Riemann sum feels a little bit closer. Is it always going to be closer? No. Is there one that's always better? No. If there was one that was always better, I wouldn't teach you the other ones. So it just depends on the shape of the curve, the way the curve moves. There's just a lot of things going on. All right, for this one, instead of going to find them for exact, I'm going to show you the function notation for it. So way up here in the beginning, I told you the function that I'm calling f of x. So down here, I'm just going to put it generically. So my first height would be f at negative 1.5, and I could go plug that in, maybe using some of my new calculator skills that I have. Plus my second height was f of negative 0.5, and then plus my third height was negative, or a positive 0.5. So this is one of the first places those calculator skills really come in handy if you store this in y1 and then go back to your home screen, and then you don't have to keep typing in that polynomial over and over and over and over. All right, those are 3 Riemann sum techniques using rectangles. And you have one more approximation technique, and that one's called trapezoid rule. Sometimes it's called trapezoidal, and I think that's fun to say, so I'm going to write trapezoidal rule. All right, in order to do trapezoidal rule, friends, you've got to know how to find the area of a trapezoid. It's really important to me that you know how to find the area of a trapezoid. It's 1/2 height, base plus base. Okay. The bases of your trapezoid are the parallel sides. So we're about to go draw 3. Again, we'll do 3 trapezoids just to be consistent. It doesn't have to be 3. These values that I have started and stopped you at are going to change. But we're going to do 3 again, just to be consistent. And what you're going to see is that your trapezoids are sideways. All of our trapezoids are going to look like this. The base is going to be on the x-axis. No, I'm sorry. The height is going to be on the x-axis. And the bases of your trapezoid are these parallel sides that go up to your function. Maybe it would help if that was a straight line, but it's not going to happen. Okay, so if I start at -2 and I go to -1, I'm going to draw a trapezoid between those two. So here's one of the bases. Here's the other base. There's my trapezoid. I know it doesn't look like a trapezoid. It looks like a triangle, but that's because this base has a value of 0. Then I'm going to do it again. I'm going to start at -1 and go to 0. Here's that height or that base value. Here's that base value. Connect the dots. I made a trapezoid. This one's going to actually look like a trapezoid. You'll like this one better, maybe. Start at 0, go to 1. There's one base. Here's the second base. And I connect them with a straight line, as straight as I can manage. That's pretty good. So we're going to add up the values of the areas of these trapezoids. I'm going to continue to call these triangles trapezoids. I'm sorry if that hurts your heart, but you need to know that even though they have a base of 0, this is trapezoid rule. We're making trapezoids. Okay, so here's what we're going to do. 1/2 is 1/2. The height of all of these is 1 still. Remember, the height is that piece along the x-axis. So this is your height. This would be your base. I'll call it base 2. This would be your base 1. Then, I mean, it just depends on how you want your brain to function. I want to be efficient here. So I'm going to go and combine things where I can. So my first base value would be this one, if I just read left to right, and that one had a height of 6, a base of 6, plus this value. I know it's 0, don't worry, I know it's 0, but it got used twice because it got used in the blue trapezoid and it got used in the red trapezoid because those two trapezoids share that side. So in my calculation, I'm going to go double that one. Not super exciting because it's 0. Okay, what about this one? So this base value, this side of that trapezoid, gets used twice. So again, I'm going to go double the value of that base. And then my last one is a single because it's the outside edge. It's the outside side. All right, I said it. So a negative 24 there. This is another place. This is fine, and that was super fun. But I picked a function, I picked a polynomial where like these height values aren't terrible. And I can type that in, and I'm not scared. It'll be okay. But you could have some really terrible numbers here. It just depends on the function and how things are broken down. And I was very nice to you to let those heights be 1. They could have been like 1.7 or 3/2 or something terrible that you hate. Please use your calculator to type in numbers. So if you want to see this in function notation, it would look like this. You would have f of negative 2, because that's your start, plus double. Your next one happened at negative 1, plus double. Your next one happens at 0, plus single. Your last one happens at 1, because that's your ending. And that is super easy to type in if I have my polynomial saved in y1 in my calculator, that x cubed minus 13x minus 12. And then I don't have to, worry about dropping a negative or any of the terrible things that happen. Okay, that was a lot. Let me tell you what's coming. So you're going to have a couple days to get this in your brain. We're not moving on immediately tomorrow, but you're going to have to practice working these questions 3 different ways. So they might give you a graph and you can go pull values off the graph. They might just have given you the function and then you have to go either graph it yourself so that you can see a picture or just know to plug in your function notation. The other thing that they might give you is a table, which in my opinion is the same thing as giving you a graph because we're just pulling them off. So please go do Delta. Delta makes this really interactive and very friendly. Delta is also going to talk about something that I'm not really saying, talking about if things are overestimations or underestimations and how come. We drew pictures and they were really pretty, but there's reasons behind all of it. So please go do your Delta for these things. All right, let me know if you need anything.